Today's applications are evolving. Organizations are building modern, cloud-native, AI-assisted applications that require massive scalability. And these aren't static workloads. As usage grows, they need to handle increasing data volumes, more complex processing, and more users, all while maintaining performance, reliability, and cost efficiency. Scaling matters, and with Azure SQL Database Hyperscale, scaling works differently. You can start small and grow large on the same database platform. Storage auto-scales as your demand grows, all while you keep the same SQL foundation. Bob, can you tell us a little bit about the underlying architecture and what it enables?
Yeah, thanks, Anna. The magic of hyperscale is the separation of compute and storage, components that scale separately but work together. A primary replica, which is where read-write workloads happen, have a buffer pool and an actual SSD cache. A second layer called page servers cover the rest of the database, partitioned together to provide that extra layer of caching. At the bottom level is the actual database files themselves stored on Azure Storage. The log itself is stored in a separate log service that has caching and scales independently. You can have HA replicas for better failover. Those replicas and page servers pull their changes from the log service to make sure data is up to date. One of the superpowers of hyperscale is a concept called named replicas, up to 30 of them. They support read scale out. And what's amazing is, for cost savings purposes, is your read workloads can use named replicas with a separate compute configuration from your primary. And finally, because the database files are in Azure Standard Storage, we can use snapshot backups, allowing amazing point-in-time restores, think of like terabytes in minutes. Combined together, that is the story of the hyperscale architecture.
Thanks, Bob. To further support scalability, Azure SQL Database Hyperscale runs on high-performance infrastructure, including AMD EPYC Compute, optimized for enterprise and AI workloads. This architecture enables us to achieve some really impressive capabilities like 128 terabytes of storage, 192 vCores, 30 named replicas for read scale on the fly, 4.5 nines of availability, and high throughput. And by the way, we're constantly working on expanding these. Now, I can't forget to mention serverless, which allows you to auto-scale and only pay for the compute you need, and elastic pools, which are used for resource sharing. Now, Bob, I know you have a demo for this, and I'd love to take a look at it.
Now consider this example, Zava Lending. They have an external customer website where they need to handle things like loan eligibility and loan applications. In addition, they have an internal dashboard to support operations of the actual business. They need a database that can scale to their current needs for both external-facing operations and the internal customer operations. Hyperscale can actually do that. What we'd like to do is simulate a workload. Simulate the workload of Zava Lending for both these operations. So we took a look at the transactions that power both the customer website and the internal actual dashboard itself. You can see here from this example, these are all OLTP type transactions. So we knew that we could handle them at least where they start with 250 users. We wanted to go further. We wanted up to 2,000 current users that we could simulate and up to 6 million transactions. We wanted to do some optimization. We took a look at the workload and decided that we could add column store indexes to specific places where range scans are being used to read data. In addition, Zava Lending has nightly ETL needs. So we need to make sure that we can support these batch operations. This is where our log throughput will really come into play. Let me show an example of a dashboard that we built that shows a simulation of this transition from 250 users to 2,000 up to 6 million transactions. Here's a dashboard that we built. We ran this workload over time to simulate this progression for these user counts and transactions. And it looks something like this. The dashboard shows the amount of vCores currently being used for this workload phase, the number of concurrent users, and transaction workloads like what is the rate per transaction or query per second transaction. Finally, a look at the actual number of business transactions representing both that customer site and internal site, the number of CPUs that are being used and CPU utilization, and really importantly, what was the actual performance, the elapsed time of these important transactions. In addition, in the final phase, we'll look at log throughput and information about column store. You can see the numbers at 32 cores, what their business looks like. When we try to go scale the business to 500 users, you can see with the current number of vCores that we have performance problems. So we can easily do an online operation to scale them up to 64 vCores and achieve that great predictable performance even as users and transactions increase. And you can see there are various phases that we can go through here for the business to up their number of users, up number of vCores to handle it. Finally, you can come here and see that at 2,000 users out of 128 vCores, they have a certain number of transactions, but not enough to support the business needs that they want or the performance that they need. So finally, we can move to 192 vCores and achieve that rich sweet spot. 6 million transactions, 2,000 users, great CPU utilization, and great response to the business transactions that they have. And finally, in the final phase, we demonstrated that their ETL job can easily run, supporting up 5 million rows loaded each night because of those log throughput numbers that we can support for those kind of transactions. Anna, what do you think?
This is a great example, and I love the visualization. But what's the bottom line?
Well, consider this as we looked at the simulation of their workload for their business. So number one, we gave them a predictable cost per transaction. Sure, their costs go up as they use more compute with Hyperscale, but the cost per transaction is the same. Super important to the business itself is linear scaling. We proved over time as we went to those final vCore numbers that those transactions should scale to make sure we meet their business needs. And lastly, most important, is the responsiveness of Hyperscale is consistent the same no matter if there's 200 users or 2,000 and up to those 6 million transaction numbers.
The key takeaway is that scaling with Hyperscale doesn't require complex planning or constant tuning. You can start with what you need, adjust as demand changes, and maintain performance along the way. That gives you a database that grows with your application instead of becoming a constraint. Thanks so much for watching this video. Check out the link below to learn more.